The first condition, which is very standard, is this. They assume this is finite. That is, this series is summable. Now, if this series is summable, does it imply that there is something called, something like a theta infinity, let's say, so that will go to 0 as n tends to infinity? So, will this condition imply this? So this condition, my question is whether this condition implies an existence of theta infinity, and whether I can prove this, that the theta n converges to theta infinity. What do you think? When can we say that there is a theta infinity such that this will happen? We have a sequence of measures. This sequence of measures are what? These are, you can view all these probability distributions, theta n's, as nothing but an element in the S-dimensional space, right? Because each one is a vector in Rs. So what is the condition that you need for existence of such a theta infinity? If you have a sequence in the S-dimensional Euclidean space, when do they converge? What is the basic condition for convergence? Huh? That's too strong. Many sequences will not satisfy that and they converge. But what is the fundamental condition that is needed, which is sort of necessary and sufficient for convergence of a sequence? Cauchy criterion, right? It has to be a Cauchy sequence. Will it be a Cauchy sequence? Can you? Why? Right. So it's like after a few finitely many terms in this series, the tail will be small. And if the tail is small, then theta n minus theta m for n and m large must be small. So this condition implies theta n is a Cauchy sequence. In Rs. And so there will be such a theta infinity. So it's stronger than that, right? I mean, this implies it's a Cauchy sequence, but if it's a Cauchy sequence, that doesn't necessarily mean that this will be summable. So this is much stronger than that. So when they are proving this result that it converges to something, so if it converges to something and then if this condition holds, then you know what will come here, right? It has to be that theta infinity. It has to be that theta infinity. Here theta infinity is just a notation, okay? It is the limit of theta n. But you need some condition on the contraction coefficients also, and that's here. So the contraction coefficient will have to satisfy this condition. Let's see. Yes. So this is one condition, and this is the second condition that you need. C of, let's say, Pk, Pn, that should converge to 0 as n goes to infinity for any k. So if all these pi's are same, then this condition is trivially satisfied, right? Because it's going to be what? It is going to be bounded by C p to the power n minus k, and because Cp is smaller than 1, for any k as n tends to infinity, that will go to 0. So these are the two regularity conditions you need, and then this will happen. So if these two conditions hold, then you have, no matter where you start, no matter what is your initial distribution. And once again, this convergence is uniform in pi. So essentially what you do is you argue more or less the way you argued earlier, but now the computation becomes a little messy, so I will not reproduce that here. So you will be able to bound that by something like a product, so that involves this contraction coefficient and the difference between pi and theta infinity. Okay. So the result that you had learned in your Markov chain theory, probably, that was about stationary Markov chain, right? That is how most of the textbooks will represent it. But that result you can actually generalize even for non-stationary or inhomogeneous Markov chains, provided these two conditions are satisfied. Okay? This is one of the results in Dobrushin's paper. Any question about what I have discussed so far? Because this will be a good time to stop for one or two questions. Or if you have any curiosity about these results, I would like to answer that before I proceed to the next thing. Because I have given you the gist of the convergence results for inhomogeneous Markov chains with finite state space. So you have a crash course on that. Okay. Normally, if I have to teach a course, I will probably spend 2 to 3 weeks discussing all these proofs and giving various special cases and examples. Okay. But this is the complete course. Okay. Yes?
Regarding the second condition.
Yeah. You mean this one? Yes.
So, if I assume that pKs are strictly greater than 0 infinitely often.
Infinitely often, what do you mean by?
I have a sequence of.
Now, I am assuming all these pKs are positive to make things simple for you.
Okay,
So that
relaxed, right?
those conditions can be relaxed, okay, but things become a little easier. So, because the kind of applications that require these results for image analysts, these pKs are all positive. So, they done. So for them, they have a much stronger condition that automatically implies irreducibility and aperiodicity, effectively. So what you really need is that all these transition matrices are irreducible and aperiodic, something like that. Any other question? Okay. Okay. So now what I will do is that I have about 20 minutes for the first session, and then I have 1.5 hours for this next session. So what I will do now, I will discuss some interesting applications of these results. So that's the agenda from now on. Okay. Let me ask you a very simple question. Usually, if I am teaching these things to some postgraduate students in a special course, I start with this question. I didn't ask it at the beginning today, so I will ask it now. Okay. Suppose you have a coin, and you want to toss it to decide whether, suppose I have two people and I have to choose between them, and I have to make a fair choice, okay? So I can't discriminate between them. So if my coin is fair, I toss it. If it is head, I choose one person. If it is tail, I choose the other person, okay? Suppose I don't know whether the coin is fair or not, okay? And you probably all know one answer to this question, that how can I use still the coin to make a fair selection? What is the answer? Anybody knows? See, I have a coin. I don't know whether it is fair or not, okay? And I have to use that coin only to make a fair selection between two people. How can I do it? There is a simple solution to this. Yes? Toss it twice and then? So if it is head and tail, then I'll choose one person. If it is tail and head, I'll choose the other person. And if it is head, head and tail, tail, then I have to do it again. So there may be many tosses that are required. Now you have this Markov chain theory. Can you use the coin to create a Markov chain that will converge to something like a probability distribution that puts probability half and half on two states? Okay, let's break this question into two parts.